So thank you very much for having me here and for giving me this opportunity to present at least a small bit of our field. As was announced, the topic of my talk is the origin of mass as seen from the lattice, and this may be a somewhat enigmatic title, which I will try to clarify during my talk. So the field of Lattice Qcd, or lattice quantum chromodynamics, has been undergoing transformative changes in the past 5 or 10 years. And it has now become possible to actually solve the equations, which I will present to you later, of quantum chromodynamics in the highly nonlinear regime, and provide reliable and precise results for many, many quantities of interest in particle and nuclear physics. So the range of topics covered by Lattice Qcd is really large. It ranges from phase transitions in the early universe to the assembly of nuclei today. And in passing, it also is used for searching for new fundamental physics in particle accelerators. But I won't have time to cover all of these subjects. And so I invite you to either look at our program list or consult people who are part of our program to learn more about these other aspects. And so what I'm going to focus on today is the relationship of non-perturbative QCD and mass. So in particle physics, we usually associate the Higgs as the origin of mass. But as I will show you today, non-perturbative QCD plays an important role also in this relationship of energy to mass. And so one way of seeing this is to consider the pie chart, which describes the mass-energy balance of the universe today, as measured mostly by the cosmic microwave background experiments such as WMAP and Planck. And so this is the total energy mass of the universe. And if you look at this pie chart, there's 68.3% of dark energy. There's about 26.8% of dark matter. Dark meaning we don't know what the hell it is. And then there's a small sliver, which is 4.9%, of ordinary matter. Okay, and this 4.9% is actually particularly important to us because it's what forms the whole world around us, so Earth, Sun, etc., and ourselves. So even though it's a tiny portion, it's an important portion. And as I will show you, actually QCD is responsible for most of the mass of this ordinary matter. Responsible. More surprisingly, non-perturbative QCD, again, which I will define in a minute, can also give us information about dark matter. And that's because dark matter experiments are trying to detect dark matter by having dark matter interfere with ordinary matter. And this interaction requires being able to understand the non-perturbative QCD dynamics. So it helps us here. And then it also gives us way too much dark energy. And that we have no idea how to solve this problem. On the other hand, it doesn't really make too much sense to talk about the contribution of QCD to dark energy in the sense that we don't really know what dark energy is. Okay, so this is sort of the first aspect that I'm going to cover, is explaining to you how QCD is responsible for most of the mass of ordinary matter. And QCD is also important for determining the coupling of quarks to the Higgs. Light quarks. And so if you draw a proton, it's in a simplified picture composed of two up and a down quark, which I will describe to you how they interact. And so the coupling of the light quarks correspond to the mass of the light quarks. So MQ coupling of Q to Higgs. And the point is that the mass of the quarks is much smaller than the mass of the proton. And so in order to dig out this very small effect, you have to be able to understand all the interactions that go into making a proton. And then the third, so this is the second aspect that I will cover. And then the third aspect has to do with the tiny neutron-proton mass difference. Okay, and as you may know, the neutron and the proton have very similar masses in the following sense: that the mass of the neutron minus the mass of the proton is equal to only 0.14% of their average mass, which I will call Mn. Okay, so this is a tiny effect on the scale of the proton and the neutron. However, it's just what you need in order to explain two important facts. The first is Big Bang Nucleosynthesis. This is a formation of elements in the early universe, so heavier elements. You start with protons and neutrons, and you synthesize elements up to helium and a bit higher. And so here, delta Mn is small enough to induce Big Bang nucleosynthesis, but it's also large enough to forbid the following process: a helium atom, which is a proton with an electron around it, from disintegrating into a neutron in an electron neutrino line. So this ensures stability of atomic matter. Okay, so these are the three subjects that I'm going to cover in the remainder of the talk. And now I'm going to try to explain a bit of the different, explain some of the different terminology that I've been using here. So here I just have a quick reminder of particle physics. Just to set the scene. So here we have an atom whose size is about an angstrom, so 10 to the minus 10 meters. It's composed of a nucleus, a small nucleus, and then it's surrounded by electrons. If you look at the nucleus, which is about 10,000 times smaller. It's composed of neutrons and protons, whose size is about, again, 10 times smaller. And then if you look inside the proton, you see quarks. There are two ups and a down. And these, as far as we're concerned, are elementary. So they have no substructure. Even though there are theories which speculate this experimentally, this is the smallest thing we've seen. And the electron falls in the same category. So these fundamental particles are described by the standard model of particle physics. So here we find the up and the down quark, which constitute ordinary matter, as well as the electron. And then the neutrino is something which appears in nuclear beta decays. And then there are two more massive copies of this, what we call a family, whose origin we don't really understand. And then there are particles which induce interactions. So there's a photon, which gives you electromagnetism, the gluon, which gives you strong interactions, and these two give you a radiative decay, so these are weak interactions. Okay, and so as I will describe to you, there's a formalism, mathematical formalism, which describes all of these particles and interactions. And here we're going to focus mainly on QCD. So QCD, and we will also take in, so essentially we will focus on these first two rows, not saying too much about the two more massive families because we're mostly interested here in ordinary matter. So then I can tell you more precisely what QCD is. QCD is a fundamental theory of the strong interaction. Its degrees of freedom are the quarks, U, D, S, and the gluons. Okay? And they interact through something called color, which is just a name to describe a rather abstract quantum number these particles have. So instead of having electrical charge, they have color. I will explain to you what the difference between these things are. So as we saw, it's responsible for a wealth of phenomena. Wealth of phenomena since the beginning of the Big Bang. So for instance, if you're interested in times smaller than 10 to the minus 6 seconds after the Big Bang, it describes the behavior of the plasma of quark and gluons. So this is the quark, gluon plasma. At around t equals 10 to the minus 6 seconds, you have a crossover and not a phase transition, and this is something that the lattice has shown. You have a crossover to quark gluon plasma to a universe that, instead of being constituted of a soup of quark and gluons, is constituted of proton, neutron, and other hadrons. Then, from about t 10 to the minus 6 to 20 minutes after the Big Bang, then the strong interaction essentially is responsible in large part for the synthesis of larger elements. So this is Big Bang nucleosynthesis. Okay, and since then, it provides the energy that we have in stars and in nuclear power plants, so energy plants. And it also is responsible for many other things like exotic phases and neutron stars, etc. And it does all of this with only 4 parameters for ordinary matter. There's a coupling constant, alpha strong, which is the equivalent of the electromagnetic fine structure constant, g squared over 4 pi. And then there's the mass of the up, down, and strange quark. Okay, you have to include the strange because of its quantum fluctuations. These are significant also for ordinary matter. And then if you are interested in the other generations, and then there are three more for C, B, and T. But so with only 4, and perhaps 5 parameters, you can go a very long way. So more mathematically, QCD is a part of the standard model. So the standard model of particle physics is what we call a gauge theory. And I won't go into the details here, but it's a theory which has theories which have large degree of symmetry. And the symmetry is described by the following gauge group. Okay, so these represent transformations on the quantum numbers of quarks and gluons. QCD corresponds to the SU3, and then QED is a U1 subgroup of this other group. Okay, and so QCD is just a generalization, so it's very much the same formula as generalized. So here we have a rather simple group. So these are transformations which commute among C cells. Here we have transformations which don't commute. And so but other than that, it's very much the same idea that goes into this. And so if you compare the types of interactions with QED have, they interact electromagnetically, so say the quark here. Quark, you have a photon, they interact electromagnetically through the photon, and this coupling is proportional to the charge of the quark. QCD has very much the same thing. You have a gluon interacting with quarks. Here the coupling is called G. But because of this more complicated nature of the gauge group, you also have gluon-gluon interactions proportional to G, and also a 4-gluon vertex, which is proportional to G squared. Okay, so it's very much the same formalism, but there are differences in interactions. And this may look like not much to you, just difference in squiggles, but it actually makes a huge difference. As a famous member of the audience showed in 1973, the fact that these interactions are present lead to two very, very interesting features of this theory. The first is called...
Yeah, can I ask some questions?
Sure.
So as time increases, actually the energy scale of the universe will decrease.
Yeah.
So at what time will the Higgs boson, will the Higgs field come in?
It's way before this. I forget the exact number. Yeah. So it corresponds to... This is a scale of about a few hundred mega electron volts, the Higgs boson is 1,000 times higher.
I see. So there the quark will already be massive in.
Yeah, absolutely.
I see. And also from step 1 to step 2, actually looks like it's a confinement transition.
Yeah, that's it. That's what I mean. Yeah.
It's a crossover.
It's a crossover. Yeah, this has been shown in Lattice Qcd actually. So for the physical values of the quark masses as they are, it is a crossover, and therefore the universe didn't boil at that point. It's just smoothly transited between the two. So we have asymptotic freedom, which is 1. So this is gross Pulitzer, and we'll check, or I sort of inverted these names, in 73. Okay, and this is an amazing property, the following thing. So let me try to draw this more or less to scale. So if you look at the strength of the coupling between quarks and gluons as a function of the relative momentum of these two particles. Here you go from 1, here you go from about 100, so this is a logarithmic scale. And we're talking about GeVs. Okay, this coupling, 0.4. So this one is not logarithmic. 1, you find that this coupling falls off logarithmically. Okay, so this was a prediction made by Gross, Pulitzer, and Wilczek, and this has been widely verified by experiment. So there are all sorts of experiments at different energy scales. It's still seen at the LHC. QCD predicts this behavior perfectly. Now, if you go to look sort of at the flip side, and you go to low energies, you find that actually the coupling grows. And it actually grows significantly, and the quarks and gluons start interacting very nonlinearly. And this leads to what's called infrared slavery. And infrared slavery, one way to see it is if you take a quark and an antiquark, and you separate them by a relatively large distance, the field lines between these two quarks, so the color field lines, instead of spreading out over the whole board, actually form a flux tube, a tube of constant energy density. And this tells you essentially that as you try to separate, it costs more and more energy. It tells you that the potential between a quark and an antiquark is linear. Okay, and this leads to the phenomenon of confinement. And as you can imagine, this is a highly nonlinear process. So if you can't just exchange one gluon, you have to exchange an infinite number of gluons. Okay, and this is where Lattice Qcd comes into play. I will abbreviate Lattice Qcd as such. So what is Lattice Qcd? So if you start looking at the theory, QCD, you see that you need more than 104 real numbers per point of space-time to describe ordinary matter. Okay, so this means that in our continuous space-time, you need an infinite number of numbers, and clearly that's very difficult to calculate with, especially on a supercomputer.
Where did you get 104 from?
Okay, you just count the number of degrees of freedom. So you count the number of gluons, the number of quarks, and the number of components, all the spins and colors, etc. You come up with 104. And 104 includes the strange. If you want to take into account the charm, bottom, etc., you need more. Okay, so just a counting of the number of numbers your theory requires to describe ordinary matter. So you have an infinite number of numbers, and therefore you have to simplify the theory, at least temporarily, in order to be able to calculate. And so this is what you call regularization. maybe with a Z here in the U.S.
With a Z in the U.S.
Okay, sorry, yeah. Well. So regularization. And so actually Lattice Qcd is just a regularization of Qcd. So what we do is we replace continuous space-time by a discrete set of points. Okay, so this is now space-time. So Minkowski space-time becomes a Euclidean lattice of points. Quark fields are only defined on the sites of the points, and then gluons is called U. Okay, here's notation. You don't need to. This is the gluon field that lies on the links between these two. Now, this lattice has a minimum distance. It also has a maximum size, so this could be time length. Okay, and so now we have a theory which has a totally finite number of degrees of freedom, and therefore we can calculate. So this provides a perfectly well-defined theory. And so now the way you compute observables, and so this is a little bit mathematical, but okay, just to give you an idea. So you're interested in the expectation value of an observable. This is O, not 0. You have to integrate, okay, I wrote it like this in my notes, over all possible link configurations, over all possible quark configurations. And then Feynman told us what to weight this integral with. You have the gluon action. Then you have, sidebar. This is the quark action with the interactions to the gluon. And then you have an observable. So this is a functional integral. Well, actually, here on the lattice is actually a finite dimensional, but large finite dimensional integral. Okay, and so this is what you're supposed to do. And you can see that part of this integral is just a Gaussian. So you can do the Gaussian part of the integral, and you're left with the following expression. E to the minus just the glue interacting with itself. Then you have a determinant of this huge matrix. Okay, and then you have the observable in which certain things have been done, simplified to eliminate the quark fields. And so then what you notice is that this is positive. Okay, so you have an integral over many, many degrees of freedom, on the order of 1 billion, but with a positive measure, and therefore you can use Monte Carlo methods. Okay, so here the important point is that lattice QCD is really QCD. I mean, all you've done is regularize a theory, which you have to do anytime you use quantum field theory. Nevertheless, you have to take a number of limits. You have to set the quark masses to their physical value. You have to take A to 0, so go back to continuum space-time. Okay, and that you have to do after what we call renormalization. Again with a Z. Renormalization. Okay, and then of course you have to take the box to be very large, so much, much bigger, say, than the Compton wavelength of a proton or whatever you're interested in. And then also you have to generate a large number of samplings to evaluate this integral. So actually each of these steps has a lot of theory behind it. It's also numerically complicated to approach these limits. So this represents a huge challenge, both and numerical. However, if you if you were to decide not to do this, so if not done, okay, you can only get semi-quantitative results. So what has changed in the past 5 to 10 years is that actually we've been able to do all of this, including computing this very non-local object that's determinant of a billion times a billion matrix. And so this is what has changed. And this comes from both a better understanding of how all of these limits should be taken, but also better algorithms. And of course, now we have petafault computers, so computers which are able to do a million billion operations per second. So combining all of this, we get the fact that today, at least for simple quantities, we're able to compute these quantities fully rigorously. So compute simple quantities with percent level accuracy with no ifs or no buts. So if the result we find doesn't agree with experiment, it means that experiment is wrong. No, QCD is wrong. Not that we think it will be. But this still needs many, many calculations. So you don't do just one simulation, you do many simulations. So let me speed up a bit. So I was going to tell you how we computed masses. So hadron masses, or masses in Lattice Qcd. Okay, and so what we do is we look at correlation functions of the following. So these are essentially you shake. So suppose you want to compute the mass of the proton. Well, you have an operator here, a quantum operator, which you place at time t equals 0, and you shake the system. And then you destroy this excitation at a time t with the same operator, charge Hermitian conjugate. So this has the correct quantum numbers for the state you want to create. And this, you can show that as t goes to infinity, this actually decays exponentially with the mass of the particle. And actually, what you find is everything is given in units of this A here. So for the moment, we don't know what the size of the lattice is. So then what you have to do is you have to determine A. So for that, you need to calculate another observable. Then you have to determine the quark masses, so mu, md, ms, and whatever. Okay, and for each of these, you also have to compute other observables. Okay, and so what you then have to do is study the mass of the proton as a function of the mass of these quarks, and then you have to extrapolate A to 0, MQ physical, okay, and L to infinity. And then what you get is the mass of the proton. So how did I write it here? Okay, you get the mass of the proton, okay, at the physical point plus a statistical error. Plus a systematic error, which accounts for the uncertainty you have in reaching this in this limit.
Laurent, can I ask a question?
Sure.
You said you're taking L to infinity, but what about the space-time volume? You're you set it up as LT
Yes.
initially. Why don't you want the product to?
Okay, so one thing you can do is yes, you're right. So T has T is also L to infinity. T is also finite, but this finiteness you can take into account actually in extracting the mass. So what you find is that if you have periodic boundary conditions, you have contributions from copies, but these are just sequential contributions from copies. And so instead of having here an exponential, you have like a hyperbolic cosine or something like this. So these are eliminated as you extract the mass here. So this was just a simplification. Of course, T is usually taken larger than the volume, because you have to really go pretty far to make sure that you get the ground state.
And the order of the limits, did you write them in the order they're taken?
With most field theories, okay, some formulations you have to be careful of these limits, and just standard regularizations, Lattice Qcd regularizations, the order is not important. So you can look at QCD in a finite box in the continuum limit, or you can look at massless quarks and etc. Okay, well actually these two limits may have some problems. So because you have higher dimension operators, if you take the mass very small, you can have phase transitions in your system, which are artificial phase transitions and not physical ones.
Stat mech, you often do have problems. I mean, you can have problems.
No. So you had no. Sorry, I answered a bit quickly. Okay, but so you do have to be careful in taking these two limits. The infinite volume limit usually can be taken or not earlier or later.
But while you're being interrupted, it's probably worth mentioning that those four observables you have for A, MU, MD, and MS correspond exactly to the four free parameters that you erased at the bottom of that panel.
Yes.
6.
Yeah, so you have to, these are just parameters of the theory. So this is nothing you're adding to the theory. There's no additional assumption. These, you just have to fix these fundamental parameters.
4 experimental inputs to distinguish our world with the quark masses we have from some other world that had the same symmetry.
Okay, so I realize I'm going to have to accelerate a lot. So I will try to do so while keeping things clear. So the first question I was going to address is origin of mass of ordinary matter. Okay, and so ordinary matter, as I told you, is constructed of, visible ordinary matter is constructed of protons, neutrons, and electrons. And you have that, so ordinary matter, neutrons, electrons. Okay, and you have that M proton, M neutron. It's much bigger than M electron. Okay, so most of the mass of ordinary matter comes from protons and neutrons. Okay, in fact, more than 99% of it. And now, if you look at an object made out of 3 other objects like the proton, you usually could get a pretty good estimate of its mass by just adding the masses of its constituents. This is completely false for protons and in general hadrons. So here you have 3 quarks, okay, with M quark typically 5 MeV. Now if you look at the proton, U D with interactions, okay, the mass of the proton is 1,000 MeV. Okay, and so where does all this mass come from? It comes actually from the energy of the interactions. energy of Qg interactions and the kinetic energy in this system. And this, you know, and if you divide it by c squared, will give you the mass of the proton. So the mass of the proton and more than 95% of the mass of ordinary matter comes from this QCD energy in the system. And the Higgs gives only less than something like 4%. Okay, so in 2008 we set out to verify this. Of course, many other people have participated in such calculations also. And so what you do is you compute the masses okay, and we work in an approximation where the proton and the neutron have the same mass, and it's called the nucleon mass. Okay, so this is called the isospin limit. It corresponds to taking the mass of the up and the down quark equal and alpha. So this is the electromagnetic coupling to 0, and this is valid to about 1%. Okay, so this is a good approximation. So you compute the masses of the proton and neutrons. So if you remember Gell-Mann in 1964, he predicted that neutron and proton were a member of a family. This family had more companions. This is a sigma minus, sigma 0. There's also a lambda here, sigma plus, and then you have these cascade states, minus C0. Okay, and so all of these are made out of 3 quark states. They're called baryons. Okay, along this line here, these are all related by this isospin symmetry. So they have identical properties or related properties in this limit. So to 1% it's correct. You can also look at QQ bar states, baryons. So we looked actually, so in 2008, so science. 2008, we computed the mass of 12 of these. Mass of 12 of these. Okay. With the added complication that some of these particles are unstable, so you have to take into account the effects of their decay products. And so what we found that is within the accuracy of a few percent, we reproduce the experimental spectrum. Okay, so this shows you that the mechanism of QCD for generating the mass of ordinary matter is consistent and agrees with the experiment. And it's a very nice validation, I think, of the lattice method. So after this, we got interested in trying to determine the mass of quarks. Flip it here. Okay, and as I told you, they're quark masses and light quark masses. Light quark masses. Okay, and these are interested because they're essentially fundamental parameters of the standard model. In fact, as I told you, they're given by the coupling of quarks to the Higgs field, to the expectation value of the Higgs field in a vacuum. These are called Yukawa couplings. Yukawa couplings, this is, the value of this is about 246 over square root of 2 GeV. Okay, and these Yukawa couplings have a very large hierarchy, so large of YQ, Q equals U, U, D, S, etc. Okay, so for instance, Y of U, Y of T, over Y of U is of order, okay, now I have to use 10 to the 10 to the 6, 100 about. Okay, and so understanding, getting numbers for these masses can sort of help us sort out what is the mechanism which produces this large hierarchy between these generations. Okay, so 5 to 10 years ago, these masses were quite poorly known. So the particle data group, which summarizes results from particle physics, had at the mass, so this is in 2010. To 4.8 MeV. So this is the average quark mass, which is the only thing you can calculate in this limit. And then the strange quark mass has a mass which goes from, okay, I guess you can't see much, but it goes from 80 to 130 MeV, so substantially more massive. So as I told you, in order to compute these masses, these are very small effects here in the proton, and they represent very small corrections to the mass of the proton. Here we're actually helped by an interesting phenomena of QCD, which is a spontaneous breaking. So the vacuum of QCD spontaneously breaks a continuous symmetry, chiral symmetry, and this gives rise to Goldstone boson modes. So this is a spontaneous breaking of chiral symmetry. Okay, and this from Goldstone theorem tells you that you'll have essentially particles, which are called the pions, whose mass is very sensitive to the quark masses, so directly proportional. So what you do is you compute this quantity in many lattice calculations for different values of M, U, D, etc. You fix the lattice scale. You also have to renormalize the quark masses. Okay, I don't have time to go into detail here, but this means doing a whole different calculation to actually non-perturbatively renormalize. And then once you've done all of this, you can draw m pi squared versus mu d. Okay, this is 400, 300 squared. These are in MeV. This is the physical point, 135 squared. Okay, now I have to get the horizontal axis correctly. Okay, this is 3.42 going up to 30.0. Okay, so 16.7. So before 2011, so less before 11, this is what we had. And okay, and then we added. So then you had to extrapolate to the physical point, and you got this, and then we were able to fill out these points. Okay, and so many people have done these calculations, and now you find that the values of mu, d, ms bar to Jev. So this is after renormalization. You have to specify the scheme given by this. similarly for the strange quark mass, and the upshot is that they're known now to better than 3%. So let me come to my last topic, which is the ab initio calculation of the proton-neutron mass difference. And so this is work that was published this year in Science.
Can I have a quick question first?
Sure.
So spontaneous symmetry breaking usually will lead to exact massless boson. So that M pi is not zero because it's not a Goldstone boson? Or
It's a pseudo-Goldstone boson. So it's like in a spin system where you have a small magnetic field.
So chiral symmetry is already weakly broken by the mass of
Yes.
down quarks, is that right? Okay.
Yeah. Absolutely. So then we have ab initio calculation of delta M. Okay, so unfortunately I won't have time to do justice to this, but what you have to do is add to all of your calculations, you have to add electromagnetism, and there too this is proved to be a lot more difficult than we thought, at least initially, and that's because you're working in a finite box. The photon, of course, once it has this massless, so it can travel around. So you have large finite volume effects. You even have trouble defining QED in a finite box. I won't have time to go through this. But so this has been sorted out for this work, and we heard quite a bit about it here also because there are alternative formulations or way of doing this. It also required, showing a sort of new low energy theorem of Qcd and QED, which actually states that the first two leading finite volume corrections to hadron masses are actually known exactly in terms of their charge and mass. So this allows you to eliminate them essentially exactly, which actually, so you get rid of the leading corrections, and that makes the calculation possible because all you have to left is to do controlled extrapolation, small controlled extrapolation to infinite volume.
Those are known as a function of volume, or
Yes.
basically still have this periodic.
Okay, so yes, you have
box, right?
Yeah. So you can show that these corrections go like 1 over L, 1 over L squared, and these first two corrections are actually, you can show rigorously in field theory that they're fully determined by known properties of the particle. Okay, and only higher order corrections are not known. They depend on the structure of the particles, and these have to be sort of fitted away. Okay, so this proton-neutron mass difference makes the three mechanisms of mass generation come into play. There's the QCD one, which we saw. Okay, so this is just the binding energy of 3 quarks. Okay, which gives you through EO equals C squared. This gives you 95% of MP. Then you have the Higgs, 2 Higgs. Okay, which essentially you have quarks scattering off the Higgs background. Okay, and this gives M quark, and this gives you less than about 4% of MP. And then to distinguish proton and neutron, you need electromagnetism. So E and M. Okay, so this is essentially, if you look at the proton, there's energy carried in the electromagnetic field around it, and this again through E over C squared gives less than 1% of MP. Okay, so we had to deal with all these different challenges, and then do a lot of computation. So there were many things.
So just being clear, so is that the correlation function also true for the space component? Can you calculate the mass from the space correlation function?
Yes, you can also. I mean, you have Euclidean symmetry.
Okay. Also, is that true for the 1 plus 1D, or is it also true for higher dimensions?
Oof. It's certainly true in 4 dimensions. 1 plus 1D. Okay, I think yes.
1 plus 1 Euclidean. All right. People try stuff out with the Schwinger model sometimes.
Yeah. Or the Gross-Neveu model.
Sorry, so this last point is for mu equals md.
Which one?
So when you incorporate the electromagnetism.
No, you do everything at once now.
So there's now, those parameters are now different.
Yes, those parameters are now different. Yes, sorry. So, and I should say, thanks for reminding. Mu. Okay, so we do all of this. Okay, and this is what we find. So we do it for the proton and neutron, and like we did in the case of the spectrum of light hadrons, we did it for other pairs of particles which have the same, which are distinguished by isospin. So we have find the following result: Mn MP. Okay, these are just numbers, so I don't know if it's really worth spending too much time writing them. Okay, but this is a tiny effect. Okay, the mass of the neutron and proton is.
But that's your result. So
yeah,
we're writing them to show how accurate the calculation
that's
is
it.
after all. It's
so if you see, this is 5 sigma different from 0. Okay, so this is a clear indication that the effect is seen in the calculation.
First parenthetical is
statistical and systematic errors.
Okay.
Sorry. Okay, so we do it for a number of other particles. So compute 5 others. Other splittings. Okay, also including charm, etc. Some of them are actually predicted more accurately than experiment, or some haven't even yet been seen in the experiment. So sort of live in fear of finding out that our result is contradicted by experiment when experiment sees it. But for the results for which there is experiment, there's excellent agreement within errors. And so this indicates that indeed when you put strong plus Higgs plus electromagnetism, you get correct hadron masses, or you get experiment. Okay, so if you give me 5 more minutes, I'd like to add a little something. So you're actually able to show that all of this fits very well together. You're actually able to do more because in your calculation you have varied the quark masses, the electromagnetism, etc. So you can actually start asking the question, well, how would things look if these parameters were different? Okay, and so this sort of starts leading into a somewhat more, perhaps, anthropic discussion, but it also means that you have now, from the fundamental theory, at least a way to address these anthropic questions. So just a quantitative anthropics. Okay, and so what we produced, since we're not allowed to have slides here, try to draw it here. So what I'm going to draw here is a contour plot of delta Mn versus the quark mass difference, mu minus md, and alpha. Okay, so here I have alpha over alpha physical, this is 1. And my plot goes from 0 to 2. Here we go from 0. So this is a linear plot. 0, 1, 2. This is mu minus md over the same thing, physical. So the physical point is here.
M down minus M up.
It doesn't matter. I mean, I'm normalizing by the physical. So.
No, but M down is larger than M.
Yeah, but the minus sign cancels. So here, it's over the physical.
Okay.
I mean, you can write it, sure, if you'd rather.
Okay, no.
Too late.
There you
How
go.
do you explore change of sign?
I'm sorry?
Did you have to?
No, we did not explore change of sign. So we always consider mu minus md. No, we have explored a change of sign of m down minus m up because we actually have something to say in this region.
If you normalize it by the physical, it always has positive.
No, that's what I was telling him.
You normalize it by the experimental.
Yeah, we normalize it, well, by the physical value, which is a value we
So
determined
the sign
in
I
our
was worried
calculations.
about was just because I wasn't paying close enough attention.
Here.
The sign in the denominator is fixed.
Okay, so let me draw. So physical point here, and so essentially let me draw this correctly. So along this line, you have delta mn equal delta mn physical. Okay, so here you have tau. So this is the lifetime of the neutron. Along this line is about 15 minutes, which makes all of Big Bang nucleosynthesis possible. Above here,
I think Lars thinks you have less than a neutron lifetime once ago.
This is what universe he's going to live in.
okay. Yeah, I'm pushing down in this direction. Okay, so you have these lines of constant delta mn. Okay, a very important line is this line here. Oops, so my 0 has moved down here. This is 0.511 MeV. Okay, below here you have H1 goes to nu E. Okay, so this is the hydrogen atom becomes unstable below this line. So definitely can't live in here. The proton also becomes stable at some point. Then there's a small region in here where if you look at how things work, you produce much more helium in Big Bang nucleosynthesis than hydrogen, and then stars will have trouble igniting and creating heavier elements.
Stars will be fun, trust me.
Okay,
Helium's
great.
fun.
Okay.
Helium's a great fuel.
Great, good to know. And so then above here, you get all of your neutrons decay way too fast before they're preserved. So you have a universe without neutrons. So conclude, can I? Okay. So just to conclude, if I find my conclusion, so remember it. Okay, so I know why, because it's on the previous page. So anyway, so as I showed you, the Higgs gives mass to elementary particles, but QCD does give mass to a lot of other things, everything we can touch and see. To go beyond this sort of leading effect, you have to include electromagnetism, okay, to start resolving the proton and the neutron. And in order to determine the impact of all these interactions on the origin of mass, you have to be able to do non-perturbative calculations. So these calculations have undergone huge progress in the last few years. We can calculate many other things which I wasn't able to discuss with order percent level accuracy. And now with the inclusion of these effects, so mu different from md, electromagnetism, and we also took into account the charm contribution, you're going to a whole new level. So previously calculations were theoretically limited to the 1% level. Now we're going to the 1% level. So with all this progress going on, I think you can expect many more results from our community in the next few years. And if you have, so, okay. Okay, you want to applaud and those who want to. So, as most of you probably have experienced, our funding agencies are always asking us for applications. And in our field, it's sort of difficult. And so we decided to take this seriously, and we started thinking about it. And then one of us fell upon this advertisement on the web. It's a bathroom scale, which tells you the amount of body fat you have. So we thought that was interesting, and it sort of went click. And so we started doing a bit of market research, and we discovered that even though you can find bathroom scales which will tell you how much gray matter you have, how much bone matter you have, etc., none of them told you how much QCD you had in you, how much Higgs, or how much electromagnetism. So we decided to build and develop such an object. So here it is, with a photo of my collaborator from the University of Wuppertal. We actually built it, so we bought this scale here, which is an industrial scale, and we plugged it. It has a USB outlet, and we plugged it to our laptop and then coded an interface which gives you the proportion. So I really wanted to bring it here today, but then I realized I was going through airport security, and I didn't feel like missing my plane by trying to explain to this guy that this box here, that metal box that has all sorts of wires coming out of it, is actually just a physics joke, and not something that's going to blow up over the Atlantic. So I decided to, unfortunately, leave it at home, but so if you visit me in Marseille, you can definitely try. And so instead, I asked my son just before leaving if he couldn't code up a phone application for this. And so if you're interested, I have... I'm sorry? So I have an application here, and if you want to know before you go to the beach how much QCD you have in you, then you can come up here and type in your weight, and you'll get the answer.
I thought you said we could stand on your phone.
Okay. It's been stood on a number of times.
Questions. Please.
So in your calculation, if I understood correctly, you extract, you have some scale for A, for the lattice constant, which you use to calculate things, and then the results that you present are after taking the limit that A goes to 0?
Yes. So you have to remove, this is, as I told you, so I don't know if you're familiar with quantum field theories.
Yes.
Okay, so you have to renormalize them, but then you have to remove the cutoff. You regularize them, you renormalize them, but once you've renormalized, then you remove the cutoff. And so removing the cutoff in this context means taking A to 0. So we do take A to 0.
Luke? So usually when I have a bound particle, I think of the binding energy actually as the energy of the independent particles if you add them all together, and then the energy of the bound state is usually less. But here it's a funny effect that the energy seems to be more, but can you compare in some sense what the binding energy is compared to, say, to speak, loose ups and downs?
Well, that's the problem. I mean, there are no such thing as loose up and down because they're confined within hadrons. So it's a bit confusing. What you can do is by, scattering off quarks, determine sort of what their mass would be at a given scale. And these kind of turn out to be much smaller. And then all the rest has to be coming from this binding, this complicated mess. I mean, one way of looking at it is called the Bag model, which is an old model from the 70s for the QCD vacuum. And it essentially says you have a vacuum, and then the hadron somehow bores a hole in this vacuum in which the quarks move essentially freely. Okay, and so in that context, it's sort of the difference in energy between the vacuum as it would be without the hadron and the energy of the vacuum as it is in the presence of this hadron. Okay, so
that energy should go to 0 at the confinement transition?
At the confinement transition, yes. So you liberate the quarks, and so then you don't have hadrons anymore. And then you can study the masses of the quarks at finite temperature, and they will have a value which is not exactly the same one as here. So I mean, it's a good question, but it's pretty difficult to get your head around this. And part of the problem is that there's no such thing as a free quark.
Laurent, when you wrote down this path integral and you integrated out the parts, wrote out this fermion determinant, and you said it's positive for the cases you are looking at.
Mm-hmm.
But generally it will be not positive when there is a finite density of, for example, matter.
Mm-hmm.
So what are there pressing, interesting experiments which you can't answer because of sign problem? So
Yes, the experiments are astrophysical matter. I'm sorry.
Greek.
Well, no, but they don't look too much at density, finite density. There's a bit of finite density, but they're mostly going up the time direction. There's GSI. There's GSI. No, so there are experiments, but I mean the main experiments are things like neutron stars, etc. So very dense matter.
So there are definite, numbers which one cannot calculate. Like it's not like there's a lot of error bars, but they are non-vacuum.
So people have been looking at this. So one naive thing you can do is you work with essentially imaginary chemical potential, and then you sort of try to blindly extrapolate to zero, etc. Or else you can do reweighting too, which works to some extent. But then, so the upshot is you can't really go very far in the finite chemical potential, finite baryonic chemical potential direction. What you can do is work at finite isospin density, because there you have things combined so that actually the weight is the chemical potential is a positive.
All right,